All right. Hello, everyone, and welcome back to our Geophysics and Tectonics seminar series. I'm excited to announce that our speaker this week is Dr. Susannah Dorfman, also known as Suki Dorfman from Michigan State University, who will be talking to us about deep earth redox, so iron and carbon in the lower mantle. So we're going deep into the earth today. So thank you very much for joining us, Dr. Dorfman, and whenever you're ready, please go ahead.
Great. Thank you very much for inviting me to this series. So I'm going to be talking about iron and carbon in particular, because both of these are redox sensitive elements. And so these can be used to tell us important things about the story of what's going on in Earth's deep interior, in the present and in the past. So I wanted to start off by making the point about why we should care about redox processes in the mantle going down thousands of kilometers. And I wanted to show this video from the Deep Carbon Observatory. This is actually not a real measurement, but what it's illustrating is that we are every day able now to observe volcanoes erupting and emitting of volatile elements from Earth's interior, including carbon dioxide gas. And we're all familiar with how important carbon dioxide is to our atmosphere today, and how important it's been over Earth's history. The original development of Earth's atmosphere was linked to outgassing from the solidifying mantle. And today, volcanoes continue to output gases to the atmosphere. Human industrial activity is generating fluxes that are now totally dominating the carbon cycle. But over geologic time, geologic outgassing and ingassing is responsible for storing most of the planet's budget of carbon. So the fluxes and the forms of volatiles like carbon and oxygen and nitrogen that outgas depends on the chemical conditions that we have in the mantle where the magma forms, and in particular the oxidation state. The oxidation state is going to make the difference, for example, between whether we see reduced carbon like diamond or graphite, or oxidized carbon like CO2 or calcite. So deep cycling processes the vast majority of Earth's carbon, and the surface expression of these redox processes is the tip of an iceberg. So the vast majority of Earth's carbon is at depth. What happens up at the surface, what happens through volcanism is an important window into what's happening to carbon at depth. And carbon, of course, is not the only redox sensitive element, and carbon is not really a major element in the Earth overall. Up here in the atmosphere, it's important, but when we talk about planet-wide budgets of redox sensitive elements, we might care more about iron, which is a far more abundant major element, and we can use that as a proxy for what carbon and other elements are experiencing in Earth's interior. So this image is another big schematic overview from a review of all the different processes that interact between the depth of the Earth and the surface and exchange carbon, and the magnitudes of these fluxes. And these processes are carrying other materials as well. If we take a broader scale, let's zoom back a bit more to the entire Earth. It's worthwhile to think about what's a 1D view of deep Earth redox. Overall, what does the redox state of the Earth look like? So in this simple layered model cartoon of the Earth, up here at the crust, we're typically oxidized. We have oxidized carbon that forms these CO3 groups in carbonate minerals, for example. And we also have this same bonding style of carbon in pure graphite. We have these 3 different bonds around our carbon. But in terms of the oxidation state, we're looking at carbon that is bonded to oxygens, and so it adopts a positive charge. The same thing is true for iron up at the surface. Up on Earth's crust, we have iron that likes to form in an oxidized state. We have rust that is forming by oxidation of iron on our surface all the time. So for example, iron oxide Fe2O3 with iron in the 3+ state. As we go down deeper into the Earth, in general, overall, we're looking at a more reduced state the deeper we go. The extreme being our core, where we have iron alloys in the liquid form in the outer core and in the solid form in the inner core. So the iron alloy there as a neutral iron that is relatively reduced compared to what we have at the surface. And in the Earth's mantle, we typically have something that is in between. For most of the Earth's mantle, we would have iron in the 2+ state. We also tend to have more reduced carbon at depth. We tend to have more diamonds found in the mantle rather than the carbonates up at the surface. So because of the oxygen fugacity variation in the Earth, which is the availability of oxygen to participate in reactions, we're getting a different speciation of carbon and iron. We're getting different charges in the different mineral forms with depth. But this, of course, is not the only change that occurs with depth. We also talk about differences in density due to the great pressures that we have deep inside Earth's interior. So pressure variation in the Earth also gives us differences in bonding and chemistry of carbon and iron. We go from at Earth's surface having less dense forms of carbon and iron minerals. And with increasing depth, we have the thermodynamic favorability of greater density forms where we have better packing of our atoms. So we go from having the CO3 groups that we have up at the surface in either our carbonate minerals or our graphite in the reduced form to CO4 groups, which occurs both in the oxidized or reduced forms. So we have more bonds indicating a higher bonding coordination. That doesn't indicate that the CO4 is more reduced. It's just an extra oxygen 2-. And we have more bonds packed into a smaller space. So this is the diamond structure. This is the difference between graphite and diamond. And it's also a difference that we observe in carbonate minerals. We also observe higher pressure phases that involve iron and silicates. In the Earth's deeper mantle, Fe2O3 that we have in the form of hematite up at Earth's surface can be incorporated in Bridgemanite, the major mineral of Earth's mantle. This involves changes in coordination, changes in the number of bonds that form. And these things interact. The changes in bonding that we have due to pressure are affecting the type of chemistry that is going to occur and how favorable it will be. We now have a whole library of different structures that we know occur at high pressure, and we observe that those structures change the way chemistry happens. So when we get to know the details of the chemistry of our iron-bearing silicates and our carbon-bearing materials, we can work out the more complicated structure of oxygen fugacity in the mantle. So that's illustrated, again, by this cartoon on the right, which is showing that oxygen fugacity is at its highest on the surface, indicating we have the most oxygen available for reactions, and it decreases as we go down. And we get continuous changes with depth, but we can also get some discontinuous changes in oxygen fugacity that are related in these structural changes of the major minerals that like to undergo oxidation and reduction reactions. So based on this picture, we can see that there's interactions. There's things that we can learn from the iron system, which is more the major mineralogy of the mantle, about what's going on in the carbon system. Our inferences about which major forms of carbon we have in the deep mantle come in part from our understanding of what happens to the silicates. So we can predict the stable minerals that are going to be hosting these different that are going to be hosting carbon and other important volatile elements based on our understanding of the chemistry. So I've been talking so far mostly about the chemistry part, but redox also has some important effects we need to care about for geophysics. So one of the things that we're looking at here is that the redox state of iron can affect physical properties of major minerals that we might care about in terms of interpreting the geophysical signature of the deep earth and heterogeneities, and also for interpreting the dynamics, the possibilities of where material is going to go, whether it will be buoyant or sink to the base of Earth's mantle. And this is because we see that the physical properties of mantle minerals will depend on the iron oxidation state. So I've mentioned that minerals can incorporate iron in multiple different oxidation states. And here I'm going to be looking at iron-bearing Bridgemanite. So again, Bridgemanite is the major mineral of the Earth. It's more than 50% of the Earth in total. And so this is really important for understanding the mantle, in particular the lower mantle. And Bridgemanite can incorporate iron both in the reduced iron 2+ and the relatively oxidized iron 3+ forms. And this summarizes a series of studies that we did to determine the bulk modulus or incompressibility of iron-bearing Bridgemanite. So here we're looking at on the x-axis, increasing amounts of iron content. And we have a different effect of iron content if we're talking about 2+ iron versus if we're talking about 3+ iron, where we saw that ferrous iron slightly increased the bulk modulus, made it more incompressible. We found that the iron 3+ made the Bridgemanite a little bit softer, a little bit more compressible. This bulk modulus is part of what we need to know to understand seismic wave speeds. It's going to affect the P wave velocity deep within the Earth. So we were looking at these effects on the bulk modulus to see whether we could use seismology to tell the difference between reduced and oxidized areas deep inside the Earth. We've also had the suggestion that redox can affect density and thus affect the dynamics of the deep Earth. So this is an image from a combined experimental and geodynamic study that argued that heterogeneities in redox of the mantle could produce provinces that would remain chemically unmixed and distinct over geologic time. This, in general, the problem of the effects of composition and density and heterogeneities and their dynamic stability is something that we have to consider iron about all the time. This is a key problem for both iron and redox because both of these can affect density. Iron is in general going to be the heaviest of the major elements in the mantle, and so it's going to have a really key effect on density. The more iron we have, the more dense the mantle phase assemblage is going to be. Anything that increases the amount of iron that goes into the rock is going to make the rock more likely to sink and potentially segregate. So we also, though, would see that for the same amount of iron content, which is what this study was looking at, for the same amount of iron content, but different amounts of oxygen, the suggestion was that density decreases with oxygen content, and to a degree that oxidized provinces would then float to the surface and reduced provinces would sink. So what constraints do we have on what the redox state is of the deep Earth? Some of our key constraints come from samples, particularly samples that come out in volcanoes when we look at basalts or when we look at xenoliths from greater depths, such as peridotite xenoliths, or you can even think of diamond inclusions, of course, as xenoliths from even greater depth. Looking at the chemistry of these samples allows us to specifically sample the redox state of specific locations deep within the Earth. But modeling is also really key for figuring out how redox changes as we go down with depth, and also from differences based on different chemical heterogeneities within the Earth. So the approach that I'm going to be looking at here is the importance of experimentally measured speciation of iron and carbon in mantle phase assemblages. Based on experiments, we can predict where these elements will go in their at stable conditions at high pressure and high temperature as a function of their composition. And we can also see the interaction between different minerals, the partitioning of these elements from mineral to mineral. And I have some examples here as well. Here's an example of a high pressure experiment where we saw that metallic iron had formed from a silicate. And here's an example of an actual diamond inclusion where we are seeing reduced iron and iron carbide that has been trapped in the diamond somewhere at depth and then brought to the surface. Okay, so the questions that I'm going to be looking at with these experiments in this talk, one of them is, what are the oxidation states of iron and carbon in the mantle? So in my first part, I will be looking at the electronic state of iron in lower mantle Bridgemanite, the major phase of the mantle. Another question that is key here is what phases, what minerals have iron and carbon in them in the mantle? So here we're looking at the question of, is the iron in the Bridgemanite? Is it in an oxide phase? Is the carbon present as diamond, or is it present as something else? So part of this answer, we need to look at the partitioning of these elements between lower mantle phases. So I'm going to talk briefly about the partitioning of iron between major lower mantle phases. And then finally, what redox interactions occur between iron and carbon and how do they change with depth? Because these two redox sensitive elements undergo oxidation reduction reactions with each other. So we need to look at how carbon interacts with reduced iron versus oxidized iron under different conditions that we might have in the Earth, in the modern Earth versus in the ancient Earth over time. And we can use that to try to come up with models for how the Earth's redox state has evolved. All right, so in the first part, I'm going to talk about some work on the electronic states of iron in the lower mantle. So again, iron is a major element, and it is present in almost all of the major mineral phases that we have in the deep earth. This image here is an illustration of the amounts of different phases that we have as we go down in depth. Up here at the top of the lower mantle, the mantle is mostly made out of olivine. We've also got some pyroxene, and we've got some garnet. With depth, olivine goes through a series of well-known phase transitions. And then the top of the lower mantle is defined by the reaction of this set of minerals to a set of new higher pressure minerals, particularly with perovskites. We've got calcium perovskite, we've got magnesium perovskite, also known as Bridgemanite, and we've got ferropericlase, the oxide phase. And then finally, at the base of the mantle, we have the transformation of the Bridgemanite or perovskite to the post-perovskite phase. So I've highlighted in red all of the minerals that take up iron. You see I've listed all of them but calcium perovskite as holding a substantial amount of iron. And we have iron as either 2+ or iron 3+ or both in these major phases in a average composition mantle. I've also highlighted in a darker red the ones that we think are the most favorable for iron. So we see that when iron can occupy both the Bridgemanite or the ferropericlase phase, it generally prefers to be in the oxide phase. Iron, of course, doesn't have to be in only these phases in the mantle as well. These are the major minerals, the ones that are most responsible for your bulk physical properties and are most abundant. We also would have then accessory other compounds present in the mantle at small amounts. So metallic iron or iron carbide could also be present in the mantle, but are not listed as this major phase assemblage. So because we have some experimental understanding of the composition of these phases, we can see that different minerals like to take up iron in different ways. So olivine up here and its higher pressure polymorphs really likes iron 2+, but it hates iron 3+. There's almost none there. But garnet is very happy to take up iron 3+. And also Bridgemanite loves to take up iron 3+ and will take even more iron 3+ if it has aluminum available as well. And so part of our understanding of how the average redox state of the mantle changes with depth is based on our understanding of the preferred redox states of these phases and the amounts of the elements that we have on the whole. Because of these experiments, we have evidence that Bridgemanite prefers to take iron 3+ if it can. And so much so that it will produce metallic iron in order to make more iron 3+. So even if the net oxidation state of the lower mantle is on average going to be iron 2+, you can get to that average state by averaging some amount of iron 3+ and metallic iron. So here's also a summary of experiments that have measured the amount of iron 3+ in synthetic Bridgemanite compositions. So here, if we have no aluminum in the system, we cluster around having about 20% iron 3+. If we have aluminum in the system, which we do in the mantle, we have a lot more iron 3+, maybe even as high as 100%, maybe more than half for sure. So when I say that iron can go into Bridgemanite, what do I mean? So again, I'm talking about this material that is most of the lower mantle, like 80% or more, and the lower mantle being so big, it's more than 50% of the Earth. So, and here is its crystal structure. Bridgemanite is made up of an interconnected network of octahedra here that are made of silicon typically in the octahedron bonded to 6 oxygens. And then in between this framework of the silicate part, we have a larger hole where we can put larger cations like magnesium. So how do we add iron here? One thing we can do is we can take iron 2+ and we can replace the magnesium 2+. Just 1 for 1, they're the same charge, they're similar size, they exchange for each other in the structure. Another thing we can do is we can add iron 3+ in a paired way. So we substitute 2 iron 3+ for 1 magnesium 2+ and 1 silicon 4+. So that again is balancing charge. We can also do that same charge balance substitution by including aluminum in the mix. So in this case, we put the iron 3+ in the bigger site, which is a lot more comfortable because really iron 3+ is pretty big to fit in this silica octahedron. The smaller aluminum 3+ fits better, and that's part of why the presence of aluminum makes it so much more favorable to have iron 3+ in the system. Everything just fits better in the crystal structure. So then finally, we also have the possibility of taking 3 iron 2+ and converting them to 2 iron 3+ and 1 iron metal. So this also can be accommodated by, we can also keep the charge balanced as well. However, most experiments that we do of the mantle do not directly observe the electronic states of iron. And this is because it's hard to do. High pressure experiments are hard in general. And the oxidation state of iron is a lot harder to measure than the composition. And the composition is in turn harder to measure than the structure. We do have some cases where disproportion does not occur in high pressure experiments. And we have the question of how is a redox change taking place if we don't have oxygen freely exchanging with our sample during the experiment. In many high pressure experiments, we try to control the amount of oxygen by using a buffer that fixes the availability of oxygen at a specific chemical reaction. That becomes harder to do the higher in pressure we go. When we go to pressures that are relevant to the deepest part of the lower mantle, buffered experiments are really, really difficult to assemble at the very tiny experimental scales that we have. So we're really trying to move the science forward by doing a better job of directly observing as much as we can of what's really going on with the chemistry and the redox. And hopefully doing a better job with miniaturizing our experiments going forward so that we have a better control of the redox. I went over some of these different mechanisms of iron, but we should note that these mechanisms for incorporating iron in Bridgemanite are going to be favored at different pressures to different degrees. So sometimes to balance charge and through one of these reactions that adds a different charged cation, we can balance that using vacancies by removing one of the atoms that would be in order to, if we remove an oxygen or if we remove an extra cation, we will also change the charge balance of the system. But having a hole in the structure is really unfavorable at high pressures. At low pressures, we can have some vacancies, but the higher in pressure and the greater in depth we go, the more important it's going to be that our structure is really densely packed. We have some other things going on. The electronic structure of iron changes in the mid-mantle for many materials. So this change in electronic spin can affect the chemistry of the reaction. And we also need to keep in mind the chemistry of the whole system. I mentioned how aluminum is important. The amount of aluminum that is present changes what's going on with iron and its redox chemistry. The amount of silicon that is present is relevant. Whether we have a separate oxide phase or a separate silicate phase that's interacting with our major Bridgemanite phase is going to change the way elements are traded around. So I first wanted to show a series of experiments where we looked at what happens to oxidized iron subducted to the mantle. So in these experiments, we took iron oxide, Fe2O3, hematite, and added it to MgSiO3 to simulate this subduction of oxidized iron to the mantle. We did this set of experiments in a multi-anvil press in a platinum capsule, which should hope to keep things mostly reduced. And we cooked these up to pressures of the upper mantle and transition zone for 6 to 10 hours to try to synthesize something like a stable phase assemblage. And we were surprised that for these experiments, we were observing consistently that the 10 mole% of iron oxide was not completely mixing with the magnesium silicate. We had a separate oxidized iron-rich phase that coexisted independent of the runtime and throughout several of our different pressures. And this iron-rich phase consistently had a stoichiometry that was about half hematite and half MgSiO3. So we have, and this is a backscattered electron image. So we're looking at differences in scattering due to density. And we see that the bright phase where we have the higher scattering is higher density, more iron. The dark phase is relatively iron poor. Both are silicates and both have an MgSiO3 stoichiometry. So when we put all of these experiments together, we saw that this iron-rich mixture of about 50% Fe2O3 and 50% MgSiO3 in the Akimotoite structure popped up again and again at multiple different pressures. And when we compressed this Akimotoite that we synthesized to higher pressures, we saw that it transformed to a Bridgemanite of a similar stoichiometry that coexisted with a less iron-rich, more reduced Bridgemanite. So what we're seeing here is that during subduction, if we have an oxidized iron component around, it can react with the silicates to form a iron-rich Akimotoite, and then at greater depth, an iron-rich Bridgemanite. So now we need to consider the possibility of this additional oxidized phase. We have a lot of solubility of iron 3+ in Bridgemanite, but the presence of a separate iron-rich Bridgemanite indicates that we have these two structures coexisting potentially through the mantle when there's enough oxidized iron around. So the next thing that we need to look at then is how is iron behaving when it has a choice between which phase that it wants to enter, when it partitions between different lower mantle phases. So here's a set of experiments that is a little bit, we thought, more complicated. We did not expect when we initially set out with that previous set that we were going to have multiple coexisting phases. We thought we would just have Bridgemanite. But here we have set out to look at a model lower mantle assemblage where we have now both the Bridgemanite and the oxide that it coexists with. So we started with olivines. So olivines like we would see in the upper mantle, except much more iron rich. We were interested in seeing the effect of very high iron content on the partitioning behavior of iron in this system. So in this case, we were using the laser heated diamond anvil cell. We're able to reach much higher pressures up to the full pressure range that we have in the lower mantle, going up to 128 GPa, which is basically the core mantle boundary. And we wanted to see what happened when we cooked this up at these pressures and temperatures that were relevant to these depth conditions. We measured the phases that formed using X-ray diffraction during the experiment. And then after the experiment was done, we cut the charge open and looked at it with focused ion beam sectioning and transmission electron microscopy. So this allows us to get more information about the chemistry of the phase assemblage we cooked up. We would not be able to do partitioning with in situ measurements alone. So during the experiment, we see something like this with X-ray diffraction. Each diffraction pattern, we're looking at the intensity of diffracted X-rays versus the diffraction angle. And each different systematic arrangement of atoms with a repeating pattern gives us a characteristic diffraction angle. When we put together all the characteristic diffraction angles, we can fingerprint the different high pressure phases. And we can also see, based on the movement of these diffraction lines with pressure, useful things like the compressibility of the material. So when we look at this pattern, what we see are a few things. One is that we've identified all the phases. I have marked all of the peaks that we've observed with a color code here that indicates, all right, we've got the ferropericles, we have the perovskite. At the very highest pressures, we start to see the post-perovskite. In some cases, we also see some SiO2 as a free phase in the stishovite form at high pressure. And then we've also got some sodium chloride, which is the pressure medium. So it's, for the first thing is, do we understand what we see? Second thing is that we see some systematic trends. At the intermediate pressure here of 61 gigapascals, that's middle of the lower mantle, we see just perovskite and ferropericles, but at the lowest pressures is only when we see the stishovite. At the highest pressures only is when we see the post-perovskite. So we're able to use those overall differences to map out some things about the phase diagram. And this seems consistent with many things that we've observed in previous measurements. We know that the post-perovskite transition should occur at higher pressure, and that for an extremely iron-rich composition like we're looking at here, it makes sense that this transition should be pushed to a lower pressure and a shallower depth than what we would see in the typical Earth. So then for the ex situ work, here is the sample. We've dropped some water on it to make the salt medium go away, just dissolved it away. And we see the laser heated spots here form a little circular depression. We put some platinum over the top to protect the sample, and then we mill away the sample 70 nanometers at a time until we get down to the thin section that we want to look at. So we can see under an optical microscope, our heating spots have changed color due to the high pressure chemistry that occurs. And we can see the texture in the sample under the electron microscope, this surface structure. And then here is the thin section that we've cut out. This is analogous to a thin section you'd look at with an optical microscope in typical petrology. But we've thinned this down to transparency for an electron microscope so that we can transmit electrons through the sample and use electron-induced X-ray spectroscopy to see what the compositions are of the phases. So this is about 100 nanometers thick in the middle. You can see the phase separation here. You can see the bright and the dark areas. Again, this is brightness and darkness is related to density. So the lighter color is the ferropericles, which is more iron rich, and the darker color is the less dense Bridgemanite phase. This sample also, we observed many of these holes in the center. This maybe used to have sodium chloride, or maybe the grain boundaries opened upon decompression, or maybe there was some water from air from the medium that entered the sample. It's hard to be sure, but we do observe that we can see the size of the heating spot is really only a few micrometers across. The very hottest part at the center is where we take our partitioning measurements, our composition measurements in general. So this is an image from the TEM. We see we've got equilibrium textures. The shape of the grain boundaries looks nice to us. In this image, we don't really see metallic iron. And we can achieve a very high resolution to see the sub-micrometer grain sizes that are formed during these high pressure experiments. And so in the TEM, we can also do mapping of the composition. So here, this is an image taken from a sample recovered from 33 gigapascals. That's the uppermost part of the lower mantle. And because this sample is so iron rich, we have a Bridgemanite that is coexisting with both an iron-rich oxide. So here we're calling this a magnesio-wustite rather than a ferropericlase because it's really iron-rich, closer to wustite, which is FeO, than periclase, which is MgO. The excess stishovite is appearing here because we've exceeded the maximum solubility of iron in Bridgemanite. We have Bridgemanite here with iron number 37, so that's 37% FeSiO3 based on the X-ray spectroscopy imaging. At higher pressure, the stishovite disappears. And the reason why it disappears is because the solubility of iron in Bridgemanite goes up with pressure. So here we have a Bridgemanite with a higher iron content, coexisting with a magnesio-wustite, and no leftover silica. We also use the chemical compositions to measure the partitioning. So based on our data, we're able to see that the partition coefficient here, which reflects how much iron prefers the oxide versus the silicate, is going down with pressure and down with iron content. So the partition coefficient of 1 would mean that iron is equally favorable in either phase. And the lower it gets, the more it prefers the oxide. So the more iron we add to the system, the stronger partition coefficient we get, the stronger the preference we observe for the oxide. We also observe that there is a difference between the partitioning for the Bridgemanite phase versus the oxide versus the post-perovskite phase and the oxide. The post-perovskite phase in general can take up more iron in a mantle rock than the Bridgemanite phase does. So in this aluminum-free system, we were not really observing a disproportionation reaction. We were not observing iron metal in most of our experiments. We did observe iron 2+, and that it's had a very strong preference for the oxide, as we saw in previous studies. For a very iron-rich olivine composition, we had almost pure FeO forming. So that's a very high preference for the oxide, and a higher preference for iron for the post-perovskite relative to the Bridgemanite. So these iron-bearing phases are the majority of the system. And carbon is going to be available as a minor or even trace element in some places. So the speciation of carbon in the mantle is going to depend on what's going on with your bulk assemblage. So what are the questions that we're asking here? Does the favorability of redox interaction between carbon-bearing minerals and iron-bearing minerals change with depth down to the core mantle boundary? And what phases host the carbon in the lower mantle system with reduced iron? Oxidized carbon is coming down from the surface in carbonate minerals typically. So, those carbonate minerals, you've got your dolomite, which has all of these different cations in it, calcium and magnesium and iron. And when it interacts with reduced iron, that's going to potentially go through a redox exchange where it's going to reduce the carbon to diamond. So the question is, which one of these elements wants to be reduced more badly? Does iron prefer to be reduced, or is carbon going to steal the electrons? So we have many different forms of carbon that could be present in the mantle that have been observed in different experiments. We've got multiple higher pressure polymorphs of the carbonates at lower mantle pressures. So here we have a calcium carbonate from the surface with its little threefold symmetry. And at high pressures, we can get a tetrahedral coordination. If it's reduced, we have diamond, or we can have iron carbides. So we had another suite of experiments here. I see I'm running over on time a little bit, so I'll try to make this quick. We had several different suites of experiments that we ran. One was to look at how favorable the reduction of the carbonate was going to be in contact with iron, metallic iron that might be present in the mantle. Another then was to look at what happened when we added silicate to the system. Since, of course, in the real mantle, we don't just have carbonate and iron around, we've also got silicates throughout the lower mantle. And how does pressure affect this? How does temperature affect this? So again, we're using the laser heated diamond anvil cell, and we're recovering thin sections with the focused ion beam and looking at them with the TEM. We can see in situ using X-ray diffraction that we undergo reactions at all depths with this iron and dolomite. We see the appearance of iron oxide peaks and carbide peaks after we heat. And we can see this pop up in our recovered sections as well. And we see here at the center of the heating spot where the reaction is taking place, we've got an iron carbide that's formed and an iron oxide. And we have an interface here between this sandwich of the carbonate on the side and the metallic iron. And we can see the reaction at the border of the carbonate, what's happening there. So here is an image of that interface from 113 GPa. We're looking near the base of the mantle here. We see the carbonate has broken down. The blue here, this started out as a calcium and magnesium bearing carbonate. The calcium part stayed in the carbonate form. We have a calcium carbonate here in blue. The magnesium carbonate part, though, separated out, and the magnesium carbonate was reduced. We formed ferropericlase here, and we formed diamond here. So we see the magnesium carbonate breaks down, the iron is oxidized, we have no metallic iron left, and calcium carbonate is preserved. So we have a couple of different reactions that can generate this phase assemblage, but what we were really excited about here was the idea that calcium carbonate is relatively stable and could potentially be present through subduction in cold conditions, even to the base of the mantle. But the key hitch there is that what happens then when we add silicates. Because previous experiments had shown, I'm skipping through a little bit, that calcium carbonate reacts with your dominant phase of the mantle, your magnesium silicate, to form magnesium carbonate and calcium silicate. So based on this, the prediction was that if you could have a carbonate in the mantle, the only carbonate that could be present was magnesium carbonate. But based on the work of my student Mingda Liu, who just graduated this spring, we showed that at the base of the mantle, we see a reversal of this reaction where the magnesium carbonate reacts back to the calcium carbonate at the base of the mantle. So based on the both suites of experiments, this suggests to us that the calcium carbonate could be present at the base of the mantle, even in the presence of iron metal, even in the presence of magnesium silicate, perovskite or post-perovskite. We were trying to link this to the polymorphism that we observe in the carbonates, which occurs at similar conditions to the reversal of the reaction that we observed. And so based on this, we suggested that a signature of successful subduction of oxidized carbon to the base of the mantle would be the presence of calcium carbonate at the base of the mantle. So to sum up again, we're seeing that both pressure and bonding are affecting the reactions that take place, and including the redox reactions that take place at depth. So we have to consider the effects of the high pressure phase equilibria to determine the oxidation state of carbon and iron that we might have at the base of the mantle. In general, we have a need for more multi-phase experiments. Because these experiments are challenging, people typically look at one phase at a time, but this is changing. And we have to characterize these experiments as thoroughly as we can to try to determine what has happened to the redox states and the phase assemblage, and to control as well as we can using new developments in the fabrication of our samples to be able to program in before the experiment starts what the oxidation state is that we're going to get. All right, so I wanted to, of course, thank the collaborators that we worked with, and in particular, Mingda for this last part of the talk, and Jiaqiao Lu, who was a postdoc here and contributed a lot to some of the work that we were doing on the oxidized iron in Bridgemanite. So thanks, and I'll be happy to take some questions.
Thank you. Thank you very much for that talk. Are there any questions for Dr. Dorfman? And congrats to your student.
Hi, Susan. I have a question, and thanks for your great talk. So in your second project and the last project, you didn't observe the disproportion. So what's that possible reason? Because it seemed to be a very common phenomenon in the, I'm not a mineral physicist, but I heard it's quite common, but you didn't observe that for two of your projects. So could you tell me what's the possible reason?
It's certainly the most of the work that's been done on the disproportionation reaction that really clearly shows it has been from multi-anvil press work. So they have very clear evidence that this exists and is widespread at relatively low pressure, relatively shallow conditions. Some of the work that is at relatively higher pressures, which this work is, show that there is a range of depths where iron 2+ is relatively more favorable, including Dan Shim's work, showing that with eels, the disproportionation reaction becomes a little bit less favorable at some depths in the mantle. So some of that could be that in general, we're looking at systematically higher pressures here. Some of it is aluminum content. But I think that's part of what's going on.
Okay, thank you. And I have another question for your last project about the Minda's recent paper. So I don't know much about the carbonate in the deep mantle, but it seems for the surface, intrusive carbonatite is a very carbonatite rocks. Most of the time, these igneous carbonates contain silicon and magnesium at the same time. But it seems in mineral phases, in deep earth, mineral phases and experimental petrology, so these two phases cannot coexist together very easily. But when it erupts to the surface, most of the time it's combined together. It's dolomite, there is a magnesium and calcium together most of the time. So usually you can't separate them at the surface. So what's the possible reason for that?
Yeah, we do. There are several previous studies that show that dolomite is, I think the breakdown pressure is only about 7 gigapascals. So dolomite is stable for a fairly, on the scale of the whole mantle, a fairly limited pressure range. So once you get down to the transition zone and lower mantle, you can't typically have dolomite. Now, of course, that's only, when you heat it hot enough to disproportionate. There have been experiments done also just on the single phase dolomite at 300 K, where you see several different reactions, different structures. But once you get it warm enough, the stable phase assemblage is the separation of the two carbonates.
Okay, okay, that makes sense. Yeah, thanks. Yeah.
Mm-hmm.
Thank you. Are there other questions for Dr. Dorfman? Michal, would you like to ask your question? I see your hand raised.
Yeah, thanks. Really fascinating talk. Thank you very much. My question is, what happens when you take your standard oceanic lithosphere composition and stuff it down into the lower mantle?
So your standard oceanic lithosphere composition, being a basalt rather than just a simplified composition that we're looking at, for me, I was still saying like complex was looking at olivine, 2 phases at a time. But yeah, it does get more complicated if you've got to think about the whole, a whole morb phase assemblage going down. So I think that there's still a lot that we need to do in terms of systematically breaking down variable by variable what's going on here, which is why we take this simplified approach. But so for example, I mean, experiments have been done on morb where they have not seen the separate very iron-rich Bridgemanite that we saw. We looked at a more iron-rich composition and a aluminum-free composition. So we did do some follow-up there on an aluminum-bearing system to try to see whether it's, where is the limit to where we get some of these phases forming. And then we still have more work to do on that.
Thanks.
Thank you. Are there other questions? So I will ask a quick follow-up, which I feel like you touched on, but so if you're doing them as sort of separate phases, is it easy to then infer what would happen as a more complex, like if you do, I guess, each experiment separately and then try to infer what would be, the sort of total grand thing. Is this consistent? Is it easy to predict? Is this much more challenging? Since it seems like these multi-phase experiments would actually be also challenging to do. So.
I mean, in terms of the chemical perspective, the more data we have on the physical properties of some of these minerals is really moving forward our ability to produce complex chemical models that accurately predict the phase assemblage. So, some of the work that we've been doing on the physical properties of Bridgemanite is allowing us to correct for thermodynamic parameters of what Bridgemanite does. And then we can put together thermodynamic models and successfully predict these assemblages. So we did also show that updating the correct parameters is allowing us to, we can successfully get the model that is what we see in the experiments. And so, from the chemical perspective, if we're able to produce a thermodynamic model, then we can put all those pieces together. From the physical perspective, we've also had a lot of progress in the field over recent years of in being able to predict what seismic wave speeds are. But these predictions are for the bulk assemblage are only going to be as good as the input that we've got. So we're getting there.
Thank you. All right. Are there other questions? Let me check the chat.
Hi, Susannah. If you don't mind, I have another question.
Sure.
So in the beginning, you show the phases have iron in the Earth's mantle. I noticed that the calcium perovskite is only mineral doesn't have iron. Is that right?
Mm-hmm.
Okay. But since iron is the densest major elements, does that mean that mineral is lighter compared to other lower mantle mineral, or it depends on the structure?
you know, off the top of my head, I don't remember what the density is of calcium silicate relative to magnesium silicate, and how that depends on iron content. But you certainly would not expect that as you change the amount of iron in the assemblage, that the calcium phase will be affected.
Okay. I see. Yeah, thank you.
Mm-hmm.
Thank you. Are there other questions? If not, we can thank Dr. Suki Dorfman again for the wonderful talk. And I will thank you in particular. I know how challenging it is to give talks while having a kid at home. And so I thank you for balancing all of this during the pandemic. So, but very cool stuff, comprehensive study. So thank you.
Thank you.